Hello, in this lesson we will learn how to solve trigonometric equations. We will combine the algebra skills you already know, such as collecting like terms, factoring, extracting square roots, and using the quadratic formula, with our knowledge of trigonometric functions and the unit circle. We will also discuss general solutions and how periodicity affects our answers. Let's get started. In this lesson, we will learn several techniques for solving trigonometric equations. We will begin with basic algebraic methods, such as collecting like terms, extracting square roots, and factoring. We will then move on to equations of quadratic type, equations involving multiple angles, and problems that require inverse trigonometric functions. By the end of the lesson, you should be comfortable recognizing which strategy is appropriate for a given trigonometric equation. When solving trigonometric equations, our first goal is usually to isolate the trigonometric function on one side of the equation. In this example, dividing both sides by 2 gives us sine of x equals 1/2. Once we reach this point, the algebra is finished and we switch to trigonometry. Using the unit circle, we know that sine equals 1/2 at pi over 6 and 5 pi over 6 in the interval from 0 to 2 pi. However, these are not the only solutions. Since the sine function repeats every 2 pi units, there are infinitely many solutions. We account for this by adding multiples of 2 pi to each solution. The graph on the right illustrates this idea nicely. Notice that the horizontal line intersects the sine curve repeatedly. Each intersection represents another solution to the equation. As we work through the lesson, remember that finding solutions in one cycle is only the first step. We must also consider the period of the trigonometric function and write the general solution. Our first example demonstrates collecting like terms. Notice that sine appears on both sides of the equation. Whenever that happens, we usually want to move all trigonometric terms to one side. After combining the sine terms and isolating sine of x, we obtain negative square root of 2 over 2. Now we use the unit circle. Since the sine value is negative, the solutions must lie in quadrants 3 and 4. Using the reference angle of pi over 4, we obtain 5 pi over 4 and 7 pi over 4. A common mistake is choosing the angles from quadrants 1 and 2 because students recognize the reference angle but forget to pay attention to the sine. Since sine has a period of 2 pi, we add multiples of 2 pi to obtain the general solution shown on the slide. In this example, we isolate tangent squared and then take the square root of both sides. One of the most common mistakes students make is forgetting the plus or minus sign when taking square roots. Remember that both positive and negative values can produce the same square. After simplifying, we find that tangent equals plus or minus square root 3 over 4. Square root 3 over 3. Using the unit circle, we identify the corresponding angles and then use the fact that tangent has period pi to write the general solution. Now be careful here. Using sine and cosine, which repeat every 2 pi, unlike sine and cosine, which repeat every 2 pi, tangent repeats every pi. Using the wrong period is one of the most common errors students make when writing general solutions. This example demonstrates the factoring technique. We begin by moving all terms to one side of the equation so that the equation equals 0. Once that is done, we factor out the common cotangent term. Because the product of two factors equals 0, we can set each factor equal to 0 separately. The first factor produces a valid trigonometric equation and gives us a solution. The second factor leads to a cosine equal to plus or minus square root 2. Since cosine values must always remain between -1 and +1, these values are impossible. This is a good reminder that whenever you solve a trigonometric equation, you should always check whether the resulting trigonometric values are within the allowable range. After identifying the valid solution, we use the period of cotangent, which is pi, to write the general solution. This graph confirms the results from the previous slide. Notice that the x-intercept occurs exactly where our formula predicts they should occur. Graphs are extremely useful because they provide a visual check of our work. If the graph and our algebraic solution agree, we can be much more confident that our answer is correct. Many trigonometric equations can be treated just like quadratic equations from algebra. Whenever you see a trigonometric function appearing both squared and to the first power, think of it as a quadratic expression. In these examples, we can treat sine x or secant x as if they were a variable and then apply familiar algebraic techniques such as factoring or the quadratic formula. This idea will be used repeatedly throughout the remainder of the lesson. Let's apply the idea from the previous slide. Notice that this equation is quadratic in sine x. Since it factors nicely, we begin by factoring. After setting each factor equal to 0, we obtain two simpler trigonometric equations. One equation gives sine x equal to negative 1/2, while the other gives sine x equal to 1. Using the unit circle, we identify the corresponding angles and obtain three solutions in the interval from 0 to 2 pi. The graph on the right confirms our work. Notice that each solution corresponds to an x-intercept of the graph. Whenever possible, it is useful to connect the algebraic solution to the graphical representation. This example contains both sine and cosine. Whenever possible, it is often helpful to rewrite the equation so that it contains only one trigonometric function. Here we use a Pythagorean identity to replace sine squared with an equivalent expression involving cosine. Once the substitution is made, the equation becomes quadratic in sign and can be factored. After setting each factor equal to 0, we obtain cosine equal to 1/2 and cosine equal to 1. Using the unit circle, we find the corresponding angles and then write the general solutions by adding multiples of 2 pi. Notice how converting everything to a single trigonometric function transformed what appeared to be complicated into a familiar quadratic equation. This example is slightly more challenging. The equation contains both sine and cosine, but neither function is squared. Because of that, we cannot directly use the Pythagorean identity. To create squared terms, we square both sides of the equation. After simplifying and applying the Pythagorean identity, the equation becomes factorable and we can solve it using algebraic techniques. However, whenever you square both sides of an equation, there is a risk of introducing extraneous solutions. An extraneous solution is a value that satisfies the transformed equation but not the original equation. That is why we must always check our answers after squaring. In this example, one of the solutions must be rejected because it does not satisfy the original equation. This is a very important concept and one that appears frequently in algebra and trigonometry. Now we turn our attention to equations involving multiple angles. Notice that the trigonometric function contains 3t rather than simply t. A common mistake is dividing by 3 immediately. Instead, treat 3t as a single angle and solve the trigonometric equation first. Once we determine the general solution for 3t, we divide everything by 3 to obtain the solution for t. Following this procedure helps keep the work organized and reduces the mistakes. Whenever you encounter expressions such as 2x, 3x, or 4x inside a trigonometric function, use this same strategy. In this example, one of the resulting tangent values is not associated with the standard unit circle angle. When that happens, we use an inverse trigonometric function. The inverse tangent function tells us which angle has tangent equal to 3. You can use a calculator to approximate this value if necessary. The other solution comes from a familiar unit circle value. After identifying both solutions, we use a period of tangent to write the general solution. Inverse trigonometric functions are especially useful, and when exact values are not available, inverse trigonometric functions are especially useful when exact values are not available from the unit circle. Our final example demonstrates the quadratic formula. Notice that this equation is quadratic in sine x. Although it is quadratic, it does not factor nicely using integer factors, so the quadratic formula is the most efficient method. After applying the formula, we obtain two possible values for sine x. Before continuing, we must check whether those values fall within the range of the sine function, which is from -1 to +1. One value falls outside that range and must be rejected immediately. The remaining value is valid. so we use inverse sine to find the corresponding angle. Because the sine value is positive, the solutions occur in quadrants 1 and 2. Using our knowledge of the unit circle and inverse trigonometric functions, we obtain the two solutions shown on the slide. The graph on this slide confirms the results from the previous example. Notice that the graph crosses the x-axis at approximately the same locations we calculated algebraically. This agreement between algebra and graphing gives us confidence that our solution is correct. Whenever possible, it is a good idea to use graphing technology as a tool for checking our answers. In closing, and to summarize, solving trigonometric equations often begins with familiar algebraic techniques such as collecting like terms, extracting square roots, factoring, or using the quadratic formula. Once a trigonometric function has been isolated, we use the unit circle, inverse trigonometric functions, and the periods of the trigonometric functions to determine all solutions. As you practice, focus on identifying the structure of the equation first. Doing so will help you choose the most efficient and effective solution strategy. Thank you for watching, and I'll see you in the next lesson.